Episode 114, A Burst of Tellurium. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart, and I am sitting, as usual, around the small circular table in the office of Dr. Emily Brunsden. Emily, how you doing?
Hello. I'm very well, thank you.
Yeah, been a busy week.
Yeah, I think that's a fair call.
I saw you earlier in the week. We went for a little wander. You and me and a small child.
Yes.
Wandering around a park here in York, which was very pleasant.
It was very nice.
And for once this week, it wasn't teeming with rain, so that's always good.
No, we were very lucky. And I think you observed that the small child had become somewhat larger than your last observation point.
Look, he's still small, but he's not as small as he was. And that being the nature of children, they tend to, that's a one-way direction of time kind of thing.
It is,
They tend to get larger before they get
entropy
smaller.
In the universe observed through the growth of children.
Yeah. But since then, we have other things that we need to talk about other than the busyness of life and the growth of children. This week, we are talking about, a little bit about where stuff comes from and some research that's helped us to fine-tune some of the astronomical and astrophysical ideas of where the stuff around us comes from. And if that sounds a little bit familiar, if you're an old school listener to the Syzygy podcast, you might be thinking to yourself, hang on, didn't you do an episode way back? We did an episode 30.
Yeah, I think we're giving our listeners far too much credit.
Look, I
could barely remember what we did.
We have people who've been listening forever, Emily. Don't play down our listeners. There are people out there who remember episode 30 well because it was the 150th anniversary or something? It was the anniversary. It was the international year
of the periodic table.
Yeah. And we went through the entire periodic table from the point of view of astronomy, which just brings it down to basically just three things. Which is what? Remind us again what the three things on the periodic table as far as astronomers are concerned?
Well, there's hydrogen.
Yeah.
Quite important.
Yeah.
Lots of the universe. In fact, most of the universe by an enormous fraction is hydrogen.
As simple as you can get and still be an atom, one proton, one electron. Lots of that. Good?
Yep.
Nailed that one.
Yep. So mostly hydrogen, a little bit of helium.
Okay. So those are the top corners of the periodic table. Sorted. Yep. Lots of that. Yep.
And then we've got a tiny little sprinkling of everything else.
Everything else,
yep.
Right. If I remember correctly, in astronomy, the everything else is just known as metals.
Metals, yep.
Even though they're demonstrably not all metals.
They're
but
not chemically defined metals, but they're astronomically defined. I mean, they're just other stuff. They're the noise in terms of the actual overall composition of the universe.
It's a rounding error. It's a rounding error on the universe. If you ignore all the metals, it's just hydrogen and helium, and that'll get you a very long way. But we're not here to go over all of that again. Instead, Emily, there's been some new research. Something big happened in the universe, and it gave us some new data. What's been going on? Fill us in.
Yeah, so somewhat ironically, we're going to be talking about very specifically one of those metals, which is quite interesting.
So it turns out some of them are actually important.
Well, yeah. Maybe we shouldn't be so blasé about our metals, but we particularly found out some more interesting information about the production of tellurium.
Right. That is very specific. This is not sort of a whole category. This is one element in particular.
Yep.
Tellurium, which is element number what?
It is element number 52.
Right. So that's getting up there. Sort of halfway along the list of elements. That's specific. What's happened? Why tellurium?
Well,
what's going on?
We observed a pretty exciting astronomical event, which was called a gamma ray burst.
We've talked about gamma ray bursts before.
We have.
Incredibly energetic things.
Yes. Some of the biggest explosions we have in the universe is gamma ray bursts. So there's a very intense, short output of, everything, but light gamma rays, which are very, very energetic.
Hence the name. It's a burst of gamma rays, amongst other things. And what? What do we think this is? What? Something happened.
Yeah. So, there are two kind of ways you can make your garden variety types of gamma ray bursts. There's two formation mechanisms. One is the collapse of a massive star. So we talked about this, I think, a little bit last week when we talked about black holes and kind of what limits of how massive you had to be to become a black hole. So very, very high mass stars, when they finish their lives, go and sort of collapse on themselves to become these black holes. And then in that process, they can become gamma ray bursts. So they have these basically these enormous jets of energy that come out and that we see as this like flash of light.
Okay. So the result of just a massive, great supernova is what we're talking about.
Yeah. Enormous, just, collapse and kaboom, really, from these massive stars. But we also get them from compact object mergers.
Right.
So that means the mergers of particularly things like neutron stars. So two neutron stars are in a binary pair, and they spend, I don't know, a few billion years just sort of spiraling around each other. But as that spiral decays, they eventually smack into one another, and that causes, again, one of these enormous,
ridiculously
explosions.
Energetic things. Yeah. Which has been in the news quite a lot over the last while, particularly because they're so energetic. Those were the signals that we first saw gravitational waves.
Indeed, yeah.
Which was really exciting back, a few years.
Yeah.
I don't think I'd realised that they would be orbiting around each other for, like you just said, billions of years. Because in the animations that they put out with the press releases, it's like 30 seconds. Like it just spirals up. And, okay, sure, that's the last bit, and it's not like that. It's artistic license and so on. But yeah, billions of years.
Yeah, it takes a while. I mean, we're not just throwing these things randomly at each other, all the time in the universe. They have to slowly decay, slowly lose the energy of their orbit together.
Wow, I just hadn't really taken that on board. So yes, bottom line is what we're talking about here. Gamma ray bursts, lots of energy coming from some of the most energetic processes in the cosmos. Okay, great. But we already knew that. We've talked about gamma ray bursts before. So what have we seen?
So we've been able to go back and look at the afterglow, if you like, of this gamma ray burster. So it's a very particular one that we're talking about today. It's got a pretty cool name. It's GRB 230307A.
Very nice. Very nice. It rolls off the tongue. It's poetry.
Definitely does. And it holds a particular, I guess, crown, if you like, or at least a podium position. And that it is the second brightest gamma ray burster that we've observed.
It gets the silver medal.
Yeah.
It's up there on the second highest bit on the platform there.
Now, you'll be completely unsurprised to know that I went down, therefore, the massive rabbit hole of finding out who's the brightest.
Of course, because if you find the second brightest, like obviously the next click from Wikipedia is brightest.
Yeah, so we'll come back to that because we've touched on that subject before as well.
All right, we'll come back to that one. Can we just, first of all, who are we talking about? Who's done this research?
Oh, we always forget this, don't we? We're terrible.
Well, sometimes we forget. Sometimes we just push it back a little bit.
Yeah. So this is a really interesting Nature paper which was published on the 25th of October. The lead author is Andrew Levan from the Netherlands, but it's a huge collaboration. It's an author list as long as your arm, because sometimes you need a lot of people to be able to digest all these kinds of data. And it uses data from three big telescopes, observatories. We've got JWST, which is what we're going to talk about in terms of the identification of the chemical elements. It's got Fermi, which is the classic gamma ray space telescope, and another one called the Niels Gers Space Observatory, which is also looking at the high energy outputs. 3 different
space telescopes.
Yep.
Wow.
Yep.
We're not mucking around.
No, exactly.
Point all the things we've got in orbit. Point them in this direction.
Yeah. Well, these kind of transient events. So we have lots of different ways of observing in astronomy, and these gamma ray bursters fall into what we call transients, as in we can't predict them. So like a supernova, right? We don't know when a supernova is going to go off in another galaxy. We can't see the level of detail to say, oh, that's about to go. We better start watching that one.
Yeah, I mean, people have been looking at things like Betelgeuse for a while and go, it'll go eventually, but eventually is like hundreds of thousands, if not millions of years.
Yeah, a few million maybe.
You'd be pretty confident to be sitting there glued to your telescope all night just waiting for it to happen. Like you're going to be waiting statistically.
I mean, it's obviously not a great use of your time just to be doing that. No. But we do have a lot of very large surveys that go on that are looking for transient objects. Most of them are actually robotic and use really clever things like AI behind them to identify, hey, that thing just suddenly got bright over there. We'll send out an alert and everyone start looking.
Which is going the other way, isn't it? That's we talk about this quite a lot on the podcast, that when things happen very, very rarely, the way you get around that in astronomy is by looking at lots of things. And eventually you will see one of them happening somewhere. You won't know where in advance, but it'll happen. Yeah.
Exactly. And so it means that a lot of very large telescopes run scheduling programs where instead of kind of saying, yeah, I want, the 5th of May to the 10th of May, please, for my observations, you give the facility your parameters of, I really need to observe this target and I need these kinds of conditions. I want the moon to be over there. So you give them kind of the parameters that you need, and they will automatically schedule your observations as to where is the most kind of efficient time to do them.
Right. Okay. So they're putting together the schedule for, an observatory, a particular telescope or a particular, up there in space telescopy thing. And that can be cut up, to relatively small chunks. And parceled out.
You don't necessarily know sometimes when your observations will happen because it might depend on the weather conditions. And it might be that you're in the queue and your ones reach the top of the queue in this particular night because these conditions are perfect for your observations. Or they might be lower down because there's someone else's observations that are higher priority that need to happen with the particular conditions that are currently
and presumably these things happen sort of fairly automatically that if suddenly your bit gets bumped up the queue, that'll just happen and you'll get told about it and you'll get the data eventually.
Yeah, typically you just wake up to an email and it's like, oh, we got you for your observation for you.
Data. So it's not like you've suddenly got to jump in your car and drive down to, mission control and point the thing yourself. You just, it just happens.
Yeah, exactly.
Cool.
This isn't universal across, but it's fairly common amongst large facilities. But what it does mean also is that they can be flexible and say, hang on a minute, we've got this gamma ray burster just happened. Let's all turn and have a look and see what's going on. Right. So if you had a more regular observation that was kind of coming up in the queue, you can be completely bumped and saying, well, hang on a minute, this is a rare thing that's happening over there. We've just got to drop tools and go and look at that.
Sorry, but you just got bumped by a burster.
Yeah,
nice.
Exactly.
Okay. So yeah, little diversion there on the ins and outs of how this stuff works. But bottom line is we had 3 different space telescopes, all pointed at this thing.
Yeah.
So you can learn a lot. What were the different wavelengths that was looking in then? JWST is infrared.
Yes, and the spectroscopic observations that we'll talk about the most. The other 2 are really more the detections and the classification of the gamma ray burster itself.
Okay.
So the whole event happened in March this year. So 7th of March was when we had the burst. Depending on which telescope you're talking about and how you measure the length of the burster, it was about 200 seconds or 35 seconds, depending on how you want to measure it.
Somewhere between part of a minute and a few minutes.
Yeah, sure. Yeah. So around about that sort of time scale, which is actually really long for one of these bursters. Most of the very, very energetic, very bright bursters, we would be only expecting to see for a couple of seconds. So it's quite, that in itself is actually a real puzzle because when we talked about the 2 different origin mechanisms for these bursters being the neutron stars merging or the single star exploding. We expect the single star exploding bursters to be the longer ones. So they're talking about tens of seconds. And we expect the neutron star merging ones to be the really short ones, as in a second or a fraction of a second. But this one's a longer one, but it's still a neutron star merger. So
weird. So do we have a sense of like what happened there? They just didn't want to merge.
Yeah. Well, it seems like we do need this extra category. It's not maybe as binary as these 2 boxes, these 2 types of mergers, and therefore 2 different types of observations. This is kind of putting some more evidence that actually the longer ones can be formed by prolonged mergers. And so there's just more, I think, nuance there than perhaps the simplistic picture of it's one or the other.
Turns out the universe is more complicated than we thought.
Yeah.
Who knew?
Yeah.
Okay.
Yeah. So that's interesting actually in its own right. One of the other interesting points about this gamma ray burster is that we noticed that the location of it was slightly unusual and that it's got a host galaxy, but it's actually not within that host galaxy. It's about the diameter of the Milky Way away from it.
Okay.
So
just hanging around.
Yeah. So these 2 neutron stars, they had to have originated in this host galaxy, right? You can't form stars just in intergalactic space. You need stuff to form stars. So that means gas and dust that you need to collapse down to form stars, to go through their life cycles, to eventually produce these neutron stars because these are endpoints of a star's life.
Yeah. So the stars had to come from somewhere. They don't just spontaneously pop into existence. They're not subatomic particles.
No. So they had to go through this process of stellar evolution to end up with these 2 neutron stars in this pair. But then through some mechanism, we don't really know the details, but they got ejected from that galaxy and are now kind of drifting away.
Got flung out. But got flung out as a pair.
Yeah.
Because again, it just wouldn't be that you'd have 2 neutron stars independently flung out and then just meet each other and make a binary system. Like the odds of that are ridiculous. So these were a pair that got flung out somehow.
Yeah.
Weird.
Very weird.
Yeah.
So that's an interesting thing as well.
Okay.
That we can add into the puzzle.
So this is a cool system already.
Yeah, I'm actually, I think, telling you more about what we don't know about this system, I think, than what we do. But we'll get there. That's the nice part of the astronomy, right? Anyway, so after detecting the gamma ray burster itself, doing some measurements on the actual gamma rays, the brightness, etc., then we pointed James Webb at this, at the afterglow, and James Webb went and looked at it twice. Once about 29 days after the initial burster and once about 61 days. And this is very deliberate because when you've got 2 neutron stars that are merging like this, turns out you've got a lot of really high energy neutrons.
Well, yeah, it's in the name, right? Like you've got a lot of neutrons, you've got a lot of nuclear material all scrunched down. I mean, we talked about that like a little while ago. I think we've done over the last several Syzygys. We've talked about neutron stars and white dwarf stars being a slightly different thing. But neutron stars being this incredibly compact bundle of nuclear stuff that when they collide, huge explosion, amongst which is this incredible quantity of nuclear material. Lots of neutrons, lots of protons, which then come out of that, which means lots of nuclei. Eventually. Which is cool.
Exactly. And the fact that you've got so many, particularly neutrons, just, chilling out because they came from the neutron stars.
Had to go somewhere.
They've got lots of energy because they've just gone through this enormous explosion as part of the gamma ray burster and part of the merger. Then you get some really interesting physical processes, particularly what we call nucleosynthesis processes. So nucleosynthesis meaning just the building of nuclei. So we talk a lot about when we talk about the formation of elements in the universe, hydrogen basically just formed out of the Big Bang, right? The Big Bang happened, the universe cooled, and then you had hydrogen.
Yeah. At its simplest, a hydrogen nucleus is literally like one thing. It's a proton. It just, you don't have to build that. It's just there.
Yeah. So we call that primordial, right?
Sure.
That was basically just happened as part of the Big Bang. Bit of helium and maybe a bit of lithium.
It's like God's first design. Can we make an atom at all? Great. Good. Let's do it.
Everything else has basically been every other element has basically been formed through some kind of stellar process. So when you talk about the elements up to around about iron, then you're talking mostly about processes that happen in the fusion reactions in stars. So fusion is basically building smaller elements into bigger elements and letting off energy as part of that process. Right. So the fusion from hydrogen to helium, that's the core driving mechanism for the sun. So that fusion process happens, energy comes out, sun is fine, happy, carries on its life. But there are lots of other fusion-related reactions. You can have even cyclic reactions in fusion where you can produce carbon, nitrogen, oxygen, all these wonderful kind of, probably like the first 20 elements that you had to learn in early secondary school.
Yes, I can't remember the specific mnemonic. It was something like, here, little Beryl Brown chews nuts on Friday. That's about as far as I can remember.
Oh, wow, that's very different to my one.
What was yours?
Henry, he likes Betty best because Nancy often flirts near nasty, muggy alleys.
Oh, so that's much better
Simple
than mine.
Peter stole Clara's aunt's kitty cat.
That's much better than mine. Yeah, that works. Anyway, the point is, it's not as simple as just glomming a bunch of stuff together. There are complicated ways of slowly but surely fusing together lighter things to make heavier things.
Yep.
All the way up to, you said, around about iron, at which point it kind of stops.
Yeah, at that point, then it actually, the whole process gets flipped upside down, because when you were sticking things together with those lighter elements, you had energy coming out as part of that process. Once you get to about iron, it becomes problematic, because if you're working with elements that are heavier than that, to try and stick them together actually needs energy to go in.
Right. Once you get up to iron, you're basically at the lowest energy per proton or neutron state that you can be in. You can stick things together, and it's like, if we manage to take these two smaller things and stick them together, make a heavier thing, up to iron, that's energetically favorable. The universe likes doing that.
That can hold up a star.
Yeah. Beyond iron, you can still have stable things. We've got loads of nuclei which are stable, but iron is the lowest energy bit. So inside a star, it's kind of hard to get past iron, because that's your bottom of the hill.
Yeah, exactly. Yeah, you're not going to get any type of way of making fusion happen, which is going to give you the energy to hold yourself up against gravity by putting together anything heavier than iron. So stars just can't do it, because they need to be putting out energy to hold their own against gravity. I'm personifying stars again. It's a bad habit.
It's going to happen.
So elements heavier than iron, there's a few processes in the universe that we've identified that can build these elements, but you need to have an energy source, right? So supernova actually are really good ways of producing different types of heavier elements, because again, with supernova, you've got lots of stuff hanging around, which used to be in the star itself, and you've got a lot of energy kicking around.
A lot of energy.
So you can start to push atoms together. They can start to do these kinds of reactions.
Yeah, again, I mean, you've got all these stable combinations of protons and neutrons for much larger atoms, much heavier atoms than iron, but you need to put in that energy to get there. You've got to give it a really good kick, and a supernova is a really good kick. It's one of the best kicks we've got.
Yeah, and these processes are called nucleosynthesis, where you're sticking things together, basically, instead of fusion, which is, building something. So in nucleosynthesis, one of the main processes that we have of building these heavier elements, say sticking two lighter things together to build a heavier thing, is a process called the R process. And the R process stands for rapid neutron capture process.
Okay, and I'm guessing it does what it says on the tin. You're capturing neutrons rapidly.
Exactly.
Okay.
Yeah, so unsurprisingly, there's also an S process.
Which is slow.
Yeah.
Right. Yeah.
So we're not going to talk about S process, but we're just going to talk about R process, because this is the one that's relevant to the neutron star mergers, and particularly the tellurium. So to give you an overview of the whole process, what we've got, say, nucleus of random stuff. You can imagine, pick your favorite chemical element if you want to. Now, that nucleus because you've got lots of neutrons just whizzing around, lots of energy, those neutrons can start to stick into your existing nucleus. So you've got nucleus which would normally be balanced roughly equally between protons and neutrons. That's kind of roughly how atomic physics likes to happen.
Yeah, I mean, in the heavier ones, it tends to be more neutrons than protons, but not by ridiculous amounts.
Yeah, almost, 50-50. But as you go heavier, you do end up getting a few more neutrons. But then if you start just banging more neutrons in,
because there's lots of them flying around.
Yeah. You're not changing the actual chemical element of your atom, because
it's neutrons, not protons.
Yeah,
and the element is defined by the proton.
Exactly. Yeah. So, but what you are doing is changing the isotope, which means that you're making, every time you add in an extra neutron, you're changing the isotope to a heavier isotope. But with the R process, and this is where the rapid comes in, you're firing all these neutrons in and making this nucleus bigger and bigger and bigger with lots of neutrons. If you weren't doing that quick enough, as in if this was a slow capture process, you would have a decay which would happen, which is called beta decay, and it means basically a neutron can decay into a proton.
Right, and that's because you've got like the vast majority of ways that you could stick protons and neutrons together have either got too many neutrons or too many protons, or perhaps both, and it just falls apart, right?
Yeah.
But if you've got too many neutrons, that's unstable. There's a much better way to do a nucleus than that, and it will decay through a bunch of different processes, beta decay being a really good one, to something which is more stable, and it'll do that reasonably quickly. But you're saying in this case, there's too many neutrons flying around. It's too fast.
There's no time. Yeah.
Right.
So beta decay is a process that takes an amount of time. Time is relative, but in this case, it can't happen on these timescales.
By the time the nucleus has even thought of doing a beta decay, it's not that nucleus anymore because we've got another neutron.
Exactly. It's massive and it's really, really heavy. And so what it does is instead it kind of breaks apart and decays into two other still heavy elements, because we're not going all the way back down to kind of boron or something like that. We are staying in the heavy element part of the periodic table. But it would, instead of having that sort of a neutron just change into a proton, the whole thing just breaks apart.
Right. So it ultimately just gets too big and does fission.
Exactly.
Wow.
Yeah. So, and this is called the R process for nucleosynthesis, and we understand this is how many of our, favorite elements are actually formed in the universe.
Favorite as in?
Gold.
Gold. Okay.
Yeah, that's how you produce
gold.
gold.
We like gold. Yeah. Randomly here on Earth. It's a valuable thing.
Yeah. Platinum is another one.
Mm-hmm.
Uranium.
Similarly.
Yeah. So these kind of, they're not really exotic to us in some sense, elements, but the way they form is through this sort of fairly exotic process in a very exotic environment.
So the gold, what you're saying is the gold and the platinum and the uranium. But let's focus on gold because it's gold. All the gold here on Earth came from things like neutron star mergers?
From these kinds of processes.
Isn't that wild? Like you kind of get a bit blasé with statements about we are all stardust, which is very poetic and nice and everything. But when you start delving into that a bit more, it's like, wait a minute, hang on. All the gold that we dig out of the ground and make into stuff is from neutron star mergers or similarly ridiculous environments.
Yeah, because there's just no environment on Earth where you have that many neutrons and that much energy in the same space.
That's wild.
It'd be very worrying if you did.
Yeah, well, it would. Yes, we'd be a bit concerned.
Yeah.
But that's nuts. Yeah. Okay, good.
Yeah. So that and another one of these ones, of course, that we have to come back to is tellurium.
Right. You did mention.
Yeah.
Tellurium, which you don't come across a lot.
No.
Do we know anything about tellurium? Do we like tellurium?
Well, it's very, very rare on Earth.
Right.
Interestingly. So if you wanted to go and have a nice piece of jewellery made out of a very rare element, much rarer than gold or platinum or any of these other ones.
Like a toilet or a bathtub. Yeah.
Yeah. Tellurium is one of your bets.
Right.
Because it is exceptionally rare on Earth. Right. Although it's really, really quite abundant in the universe, relatively.
That's weird. Why would it be really abundant in the universe and not here on Earth?
So
we're just unlucky?
Well, a little bit. It's to do with how it's quite a volatile metal. So when it's in its stable form, it is actually kind of a shiny metal in the classic kind of aluminium or whatever sense. But when the Earth was forming, so when the solar system was forming, when you had the solar disk and you had all these kind of elements kicking around, tellurium was at that point in the form of a gas and really volatile. And actually, we believe it was lost to space as the Earth was forming.
Wow. So we would have had a pile of it along with all the gold and the platinum and all the other bits. But volatile, which means it's sort of gassing off into space. We lost all our tellurium. Yeah,
so there's not much in the Earth's crust at all.
Wow.
So it's quite rare.
Okay,
it's also really hard to extract, apparently.
Maybe not about.
So, yeah. So, if you want to really splash out. Maybe
listeners,
not,
if you want to send us a tellurium bathtub, we're not going to say no, I guess is what Emily's saying.
And I'm not sure if it has a lot of use apart from being a bathtub. I don't even know if it would make a good bathtub. But anyway, so tellurium is not a metal we're particularly familiar with in our everyday lives because of that.
But that's not the point.
No.
The point is we've learned something about it through this gamma ray burster.
Yeah. And it is abundant in the universe. Yeah. It's, it's kicking around. It's really important.
All ours is out there for a start.
Yeah, indeed. Yeah. And I had to kind of laugh because although tellurium is the main focus of this piece of research, they also do hint at a couple of other heavy metals, which are quite important. Particularly, they talked about iodine and thorium. They didn't talk about thulium and thallium, which disappointed me quite a lot.
There's a reference there.
There is a very good reference there that should be part of your life if it's not already.
Lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, actinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium.
So we are, let's just, little recap, okay? Just going back for a minute here. because you've covered a lot of territory with a few, as we like to do, tangents and rabbit holes. That's fine. We are looking at an incredibly energetic explosion of some kind, very long way away, which on its own is really interesting because it took far longer than it would normally take for the thing to actually happen, for the burst, right? And it's got a host galaxy, but it's not in the host galaxy. It's like a really long way outside of the host galaxy, which is weird. But we're shelving all of that because we're focusing in now on the stuff that we're looking at in the afterglow of this incredible explosion. And we are teasing out, there's tellurium in there and there's other elements. And here's a really good question. How the hell do you know that? Like, how do you know what's out there? And I know that you can look at a star and see what's in the star from the spectrum of the star. Is that what we're doing? Are we looking at the spectrum of the afterglow of this thing?
We are, but we're looking in the spectrum in a different way to how we would look in the spectrum of a star.
Right.
So we've talked about, I think, spectra of stars a few times, but as a recap, what happens is, say the sun produces what we call black body spectrum, which is it produces light over a huge range of wavelengths, and that the amount of light that's produced at every wavelength is just determined by the temperature. The most photons that are produced in the optical part of the spectrum, and that tells us that the sun is around about 6,000 degrees on the surface.
Right. Okay.
But what we do see when we look into the detail is that all those photons are being produced in the center of the sun, right? But they've got to get through all the rest of those layers to get out of the sun. And it's in the outer layers, the cooler outer atmosphere of the sun, that if you've got particular chemical species, let's say hydrogen, which there's lots of, that hydrogen can absorb very specific wavelengths of light. Hydrogen loves to absorb things like 656 nanometers.
Right. And it's very specific.
Very specific. Yeah. And so when we look at the spectrum, we see 652, 653, 654, 656 is missing.
Right. Because the hydrogen has absorbed it.
Yeah. So, and this means that each chemical element absorbs specific wavelengths in a slightly different way. We use terms like chemical fingerprint because we can then say, well, those particular wavelengths are missing, therefore it's this particular chemical element.
Right. Hydrogen and helium and all the other elements have a very, very specific fingerprint, a very specific spectrum of stuff that they like to absorb or emit, depending on which way you're looking. And so if you look at all the light coming from the sun, you've got this huge extended rainbow across all of the different wavelengths with these lines in it. And those lines tell you that's what's there.
Yeah.
And you can see that really clearly. Yeah.
And what's happening on the atomic level is that nucleus of, or that atom of hydrogen is saying that I can only accept energies or photons of particular wavelengths, right? It can't do just any random one. It has to have these very specific wavelengths that are to do with the arrangement of the, particularly the electrons in the atom.
It's the magic of quantum mechanics.
It is, yeah. But yeah, you're right. The other way works down as well. So when a atom absorbs a photon, it increases its energy a little bit, right? But when an atom randomly decays from one energy state to another, it releases a photon. And
again, that's at that very specific frequency.
Exactly the same one as the one it absorbed. So you could imagine in the life story of a hydrogen atom, it can absorb this wonderful photon at 656 nanometers, sort of hang out in this higher energy state for a while, and then release it again. That photon will be exactly at that wavelength again.
Yeah.
So when we see emission, it typically means that you're in a pretty energetic environment because it means that you've had energy that somehow built up your, let's say, hydrogen atoms into this upper energy state, and now they're decaying back to give away the photons again.
Right. So if you happened to have a whole bunch of stuff, material, elements in the universe in an energetic environment, rather than looking for the gaps in a spectrum, you can look for the bright lines in the spectrum. And you could see, oh, there's a bright line at that frequency. That's probably hydrogen or carbon or tellurium.
Indeed, yeah.
And like what kind of really highly energetic environment might you be in?
Well, you could be in the afterglow of a neutron star merger.
That would be one of them. And so rather than looking at gaps in a spectrum of a star or something else in the universe, you're looking at the actual emission lines, the bright lines from these materials themselves in this afterglow. Cool.
And the reason why we need such awesome telescopes like James Webb is that some of these lines don't happen in the optical part of the spectrum, but they happen in the infrared.
Right, which is what James Webb's all about.
Yeah, exactly. So in this case, it's the mid-infrared, and we're looking at specifically an emission line of 2.15 microns. So more micrometers, and that is linked to the element of tellurium.
Okay. And that's not coincidence. Presumably they went, well, James Webb's really good at looking at this region. What would be something that we would expect to be out there? And let's go and find it.
Yeah, exactly. So there's really a lot of unknowns to do with these nucleosynthesis processes that we're trying to understand and trying to use observations to help inform our understanding. So we need to know how fast some of these reactions happen. We don't have very good measurements of the speed of those. We need to know how likely some of these reactions are to happen, what special environments are. And whilst these might sound like kind of esoteric questions on themselves, but in bulk, I mean, we're talking about how do you build the chemical composition of the universe? So even small discrepancies in these kind of numbers can mean vastly different amounts of tellurium that you're trying to produce to match what we observe in the universe.
Yeah, I mean, we already said at the beginning that, there's hydrogen, there's helium, and then there's everything else as a rounding error, basically, on the quantity of stuff in the universe. And so if everything put together is actually a tiny amount, you can be pretty confident where tellurium comes from. But you can still be really wrong about the total amount of tellurium that's actually out there, which presumably affects all sorts of things around models of
just how the whole universe evolves, right? Chemical evolution of the universe tells you exactly how the whole the formation of everything works, like how much material is going to go into the next generation of stars or planets. What is that going to look like? How does that make galaxies evolve? How is it becomes the biggest question from the smallest atoms.
So we trained JWST on this thing, and we saw the tellurium, but that's not the end of the story. It's not just that we saw it.
Well, from these you can also figure out the abundances. Right, so you can figure out how much tellurium there is, and that allows you to backtrack and say, well, which processes are at play here, and in this energetic environment, are we seeing these particular steps in the process or other circular loops or things like that? So it becomes really useful data.
So it's getting down into that detail where you're going from, hey, this happens at all. The notion that you can have two neutron stars spiraling around and merging together in this incredibly cataclysmic event. Just knowing that at all is a good start. But then digging into that is all sorts of, but we've got all this nuclear material flinging about. How does that work? Like what actually happens there? And the best way to investigate that is to say, well, what came out of it? How much of this versus how much of that? And that tells you what are the dominant processes happening in there.
And to sidestep into another part of your world, I know that you're involved a lot with binding blocks and the nuclear astrophysics projects that happen in York and Hull and beyond.
So binding blocks, just for anyone who doesn't know, which is probably pretty much all of you, it's an outreach program based here at York, but across a bunch of different universities, where they basically look at nuclear physics, teaching nuclear physics and teaching people about nuclear physics with the help of like a 40-foot long Lego chart of all of the nuclear isotopes that are in existence. It's awesome.
It's really nice.
It's a very cool thing.
Yeah, it's really fun because you get to build basically a huge Lego chart of. It's another way of viewing the periodic table effectively. It doesn't look like the periodic table. It's just another kind of version of it, but you get to build it out of Lego.
Yeah, and like Lego makes everything.
Oh yeah, exactly. Yeah. So that's where this research has really come into play, because you can do a lot of models, you can model how all these processes work, but you always need the observational constraints to fit to add into those models to get them accurate.
Okay, so quick recap, right? Gamma ray burst.
Yep.
Weird gamma ray burst. So
Yep.
we're learning already, yeah? And then able to point JWST, which surely has paid for itself like 100 times over already. So well done, team. At gamma ray burst to measure how much tellurium is there out there. And we're learning about that and its abundance, at least in this part of the universe. And that's teaching us an enormous amount about the R process, which is cool.
Yeah.
But I want to backtrack because you said earlier that this was the second most energetic gamma ray burst that we've ever seen. And second's never good enough.
No, it's such a loaded statement, isn't it?
Obviously, the next thing you would do is, but what's bigger?
Yeah.
And so, Emily, which was the boat?
We've talked about boats before. So boats are...
We talked about goats on boats.
We did. So boat stood for Brightest of All Time.
Yep.
We decided that we hadn't seen a boat yet, I
No.
think was our conclusion. But let's recap on some of these ideas.
But we were taking all sorts of different possible kinds of boat, weren't we?
Yeah, there weren't speedboats, but there were lots of boats. So let's do a recap. So episode 61, I think it was, we looked at a claim that a black hole merger explosion was the biggest explosion in the universe. That's a long time ago, isn't it?
It is, yeah.
And now, I don't even remember from our boat episode, but I played around with the units and I ended up in a random metric of units.
Yeah, you want to talk about tangential rabbit holes. Well, I don't know where we ended up.
Oh, I ended
but
up in ergs and it was horrible. I regret it. It was terrible. I've gone down another road, and another set of units.
Good.
So it'll be maybe useful. We'll see. So in this set of units, I've gone with number of times the luminosity of the sun over its whole lifetime.
Right. So adding up all of the stuff that comes out of the sun in energy over its entire lifetime, that's one.
Yep.
Okay.
Yep.
One sun.
And if you want a more accurate number, it's something around 10 to the 44 joules.
Let's just go with one sun.
Yeah, one sun.
One sun life.
Yeah, okay.
Yep.
Now, that explosion, they were claiming it was about 10 billion one suns.
That's a lot.
Yeah.
Yeah.
It's now what you have to be very careful with here is that time matters, right? So brightness is got a time dependency, right? It's how many photons are coming and hitting your eyeball per second.
Right. I mean, if you had a really, really, really dim flashlight, torch, shining in your face, like really dim, but for the rest of eternity, that's a lot of photons over an infinitely long period of time, as opposed to a supernova going off on your eyeball. Like, they're both like lots of energy, just different time frames.
Exactly.
Right.
Yeah. So the black hole explosion we talked about actually occurred over a very long time scale because we talked about it carving a big hole in the galaxy.
That's right. Yeah.
So that number is perhaps not a particularly useful number in a sense because we're talking over really long time scales. So the amount of sort of the brightness in terms of the amount of energy per second is actually a lot lower.
Okay, bit disappointing. I mean, it did carve out a massive great void, which is impressive. Well done, points all round. But in terms of like what you really want, is a massive great explosion.
Yeah.
And that
And a
just
bright
doesn't-
flash.
Yeah.
That's
that
what
kind
we're
of-
imagining here,
It kind of
isn't it?
feels like it's getting in there on a technicality.
Yeah.
No one likes that.
No.
So let's put that one aside.
Yeah. And then, so that was episode 61. Then we also talked about the latest claim for the biggest explosion ever, which was in episode 107.
I thought it was not that long
Yeah,
ago.
not that long ago. I don't even, it's not quite in this book, but it's in the previous one. Now, this was actually, again, over an extended period of time scenario. So in terms of raw numbers, this was only 100 suns in terms of brightness over a long period of time, but a shorter period of time than the black hole explosion we just mentioned.
Okay, so we're moving in the direction of explosion-y things, but still a long period of time, but much less energy. But
Yeah.
I mean, presumably it's easier to put out huge amounts of energy over long periods of time. Like if you're going to do it in a big explosion-y type thing, that's hard to do on massive scales.
Yeah.
Yeah.
So that was the boat that we kind of
Sure.
I think we came to the conclusion it's not really a boat.
Yeah.
It looks a bit like a boat, but
Yeah.
it's
more
bit,
of a barge.
maybe. Yeah. So let's compare like for like, then.
Okay.
That might be a bit
Right.
more useful.
Yeah. Let's do
So
the thing that everyone actually wants.
Yes, gamma ray bursters.
Good.
Gamma ray bursters, some of the brightest biggest explosions in the universe. Great. This is the second brightest gamma ray burst we've ever seen. We can at least compare apples with apples.
Okay. We're just going to put a big box around it and say gamma ray bursts only in here, please.
Yes, exactly. So the brightest one we have ever seen is GRB 221009A.
Again, poetry.
We did talk about this one actually when we talked about boats as well. And this one output around about 1,000 suns.
It's a lot.
Yeah.
Yeah.
So it was quite a lot.
Yeah. In a very short period of time.
Yeah. Yeah. So we're on the scale of a few seconds. So we are actually comparing like for like in terms of
I think
time.
that's an explosion by human.
It was a lot. Now, this one, I had to do some creative maths here because nobody reports in scientific papers how many times the lifetime output of the sun their explosion is. In fact, they often don't use any kind of sensible units and very rarely will even use consistent units.
Someone should have a word. I mean, someone from PR should say, look, people want to know how big this explosion-y thing was. So put it in terms that people can understand, please. We need to have consistency here.
Yeah. So, well, there was a conversion factor, which was done for the press releases, which was this one was 1 million times brighter than the brightness of the galaxy.
Okay. I mean, how bright's the galaxy?
Well,
we can't even see all of it. So that doesn't help.
No, and it doesn't help us with suns either, which was the unit I was going with at the time.
True. Yeah.
Anyway, but my back of the envelope fudge calculation, if you like, is you end up basically about one sun. One solar lifetime output of energy is around about that level.
Okay.
Right.
Okay.
So that means that we had the brightest, which was around about 1,000. This one, which is around about 1. And so there's a big difference.
Yeah.
Already.
There's a big gap in the way.
Yeah. And all the rest of which are fractional
Right.
of that.
Okay. So this was second, but by a wide margin. It wasn't even close.
No.
Cool.
So we're not, no one's sort of trying to eke in on that gold medal that GRB 221009A has.
Well, it's been an episode of Tangents and Rabbit Holes. I've liked this one. This has been fun. I didn't know that we were going to go in these different places. I didn't know anything about tellurium. Now I know. Now I know. And I'm still keen on a tellurium bathtub. So, Christmas is coming.
We should check if tellurium reacts with water.
Is it? Well, I mean, you don't have
probably
to use
doesn't.
it. You just have
I don't know. Sodium does, doesn't it?
Yeah. Emily, if people wanted to get in touch to find out what's the easiest way to ship a tellurium bathtub to the Syzygy team, how would they get in touch with us?
So there is a really handy contact me box, contact us box on our website, syzygy.fm.
Yes, indeed.
Which is a website that helpfully has all these previous episodes. So if your memory isn't as great as all the rest of our listeners, or indeed anywhere near mine, you can go back and listen to episode 30, 61 and 107 to catch up.
If you want to go and revisit Emily's take on where everything came from and what was the boat that was bigger than the other boats and
why there were goats involved.
Why were there? I can't even remember why there were goats. But look, you can do that. And all the other episodes besides, they're all at syzygy.fm. We're also on some of the social medias, including a whole new social media, I think, since the last time we spoke. We're now on Threads.
Ooh.
Well, we were already on Instagram, right? At SyzygyPod. And Threads is like, it's the Twitter of Instagram. And so you get it for free.
Oh, I was going to ask a really embarrassing question.
What's Threads?
Yeah.
Yeah, it's basic. It's Facebook's, Instagram's, Twitter.
Okay.
So,
Cool.
Look, if you're on Threads, go and find us at SyzygyPod. We're on there doing the things. We're also on YouTube if you're the kind of person who likes to watch the things you listen to. I can't guarantee that the visuals are absolutely thrilling, but we're there anyway. So just go and find the Syzygy podcast.
Sometimes you just want calming visuals anyway.
Yeah, exactly. Listen, if you're wondering to yourself, how can I help improve the show and make it better. First of all, get in touch and say hi. You never know. If you get in touch with us and ask a question or point out something really interesting that we might not have thought about, you might get your own episode devoted to your bit of correspondence.
I think those are some of our best episodes.
They are. They're so much fun when people get in touch with us. But the other way that you can do it is just to spread the word. Go and tell everyone that you know that you think would get a kick out of having their mind blown every couple of weeks by something awesome in the universe, and point them in the direction of the podcast. Finally, if you want to actually help us to do the thing that we do financially, you can head over to patreon.com/syzygypod and throw a couple of bucks, a couple of pounds our way every month, and it helps the electrons flow through the website and helps us to do the things we do. But the most important thing is that you keep listening, and we'll be back in a couple of weeks. We'll just have to see how the schedule goes. In the meantime, Emily, it's been fun. Great to see you.
See you later.
Bye, everybody.